I will return it to you later, I promise. Actually, Eastern Lights is named after Northern Lights. The leader of all this was so enlightened by Northern Lights that said, okay, we want to have an Eastern Lights. So this is what I'm going to talk to you, and it is earlier than what you just presented. Huh? So it's not that we are going to hope too much. We are now doing the modeling for designing the experiments. So, but the question is, so they say that you have to start the presentation with a question. The question is, now you drill a hole and you find no permeability, very, very low permeability, like your kitchen, the stone on your kitchen, something like this, and say, what do I do? And this happens. It has happened several times, and then people gave up. And I say, no, you don't have to give up. That's the gist of this presentation, is that you don't have to give up. In our Eastern Lights project, we have a situation like this. But so what I'm going to tell you is what is this project about, so that Philippe knows next time, and a little bit about the site and the modeling that we are doing. So the Eastern Light projects, named after the Northern Lights, they want to be the lights of the Eastern Europe, is funded by the European Union and Holcim. This is a cement factory, a cement company. And the concept is to develop something that, like what is being developed in the North Sea. It's like a network of storage sites connected by pipes, so that you come there and you inject your CO2, and then the operator decides where to take it. So that's basically but this is the very preliminary step to that. And there are a bunch of us. So it has, a transport demonstration, a storage demonstration, with some upscaling modeling to simulate the whole network of storage sites. And a lot on stakeholder engagement. What I'm going to discuss here is just a little bit of the storage part. Just to point that, so the site is, yes, it is located in northwest Bulgaria, in an area which is, tectonically, for those of you who are geologists, this is a very exciting area, because it has been undergoing all major tectonic things, but I will not get into that, just to point that it was heavily explored during Soviet times, some 60, 70 years ago. So there are lots of data. On the left, every red dot is a borehole, and its green line is a 2D seismic line. So we have lots of data. The pinky in this PC, brownish in this one, I don't know, is the area that they are licensed for storage. And that blue thing there is the Danube River, the biggest river, the longest river in Europe, with permission of my German colleagues about the Rhine River. So anyway, so we have lots of boreholes. In many of these boreholes, we have very good logging data, so gamma ray and resistivity, so that you can get an idea about porosity. So that's why we know the porosity is extremely low. And also they had some injection tests during drilling, in some of them very poor, but to get an idea of permeability, so we know the permeability. Anyhow, we have a very good idea of the geology, of the stratigraphy, and so this is where we are going to store. In that green square is about from 1,200 meters to 1,1600 meters depth on carbonate. And it is under like 500 meters shale cap rock, so it's very well protected by the cap rock. And yes, so we have the static models and all that. And this is we have bought the place to drill the hole. We haven't yet drilled the hole. We are fighting permits. So permitting is always like a pain in the back. But for now, so this is all about the site and the states of the project. What I want to discuss now is the problem that we have. The problem that we have is that this is not just carbonate, it's recrystallized carbonate, so that the primary porosity of the carbonate has been filled with precipitated carbonate. And as a result, the porosity, 5%. It depends. We now have some cores and they are measuring it, and so there is some variability, but in between this range, 5% primary porosity. And the permeability that we derive from this injection test during drilling is of the order of 1 to 5 millidarcies, 10 to the minus 15 square meters. You were talking about the first presentation, 100 square meters, forget it. No, this is 10 to the minus 15. And that's why I say, well, it is not as low permeability as the stone in your kitchen, but almost. That's what we are talking about. We want to inject CO2 there, and so the question is, what can you do? And so what we are planning, but the thing is, CO2 is very nice, because CO2 is such a low viscosity that even in this medium you can inject CO2. And in fact, you could say, well, these are two different assumptions depending on the we are designing the whole thing. Where are we going to inject, etc. So it's going to be a mixture of these two cases. So the point is that even in this low permeability, the viscosity of CO2 is so low that you can inject it. In fact, often we have the opposite problem. We want to inject cold to have high density, because most of the pressure when you inject CO2 is to overcome buoyancy. So you want to inject it cold so that it is in liquid phase, so that its density is close to 900 kilograms per cubic meter. But to inject it cold, you need some high pressure. But it is so easy to inject it that when the permeability is high, you cannot have the high pressure. You would have to be injecting, 100 kilograms per second or something like that. So it's not so bad. Huh? It's not so bad to have a low permeability. Now the problem is, and this is the explanation, blah, blah, blah. I'm not going to go into the details of the explanation. The explanation, but basically the concept is you spend most of the pressure first in overcoming buoyancy. Imagine that you want to stick a big balloon 1,000 meters depth. It takes a lot of energy to lower this air balloon into, okay, well, this is not quite an air balloon, but almost. And the second source of overpressure that you need is to displace the resin brine. And the resin brine you will have to displace no matter what. But the problem is that, as I said before, the spirit of this project is that you have many deposits, and you deposit and you inject depending on where is the injector and what are the free spaces and what are the under maintenance or whatever. So we assume that there will be lots of, inject and stop, this type of operation. And we assume that the CO2, the brine will inject back. So you don't want to spend a lot of energy displacing this brine. So basically the point is you want to increase the permeability near the well. And this is the goal of what we want to do. Now, how do you do that? Well, we have to do a lot of testing prior to the injection. Because of time limits, it will not be so long. We will only have like 2 months because we have to meet the calendar of these impossible calendars of the EU project. But so we will have like 2 months for testing, and the goal is that on the one hand is to verify these permeabilities. The permeabilities we have are from very poor tests, so we are not really sure what the permeability is going to be. But just by looking at the logs, it is going to be very low, that for sure. So this is the first goal. The second one is to characterize a little bit the mechanics. And for that, we will be monitoring displacement with optical fiber along the casing, on the annular space between the casing and the formation. But for that, in order to have a significant displacement, measurable displacement, you have to do injection for a long time and at high pressure. And since you are doing that, we are going to do also push-pull tests. Now, the problem is you have to be very careful with the water that you inject, because you don't want to have many geochemical changes. So basically, we will extract and inject the same water back and forth several times. And so every time we inject it, we put tracers. We put both conservative tracers, you'd be interested in this, and reactive tracers. And the point is, you see the changes in chemistry versus time as you extract the water. So you inject clean water, and then you extract it, and then you say, okay, I have a lot more calcium and a lot more CO2 or carbonate, inorganic carbon, therefore I have dissolved calcium, Nobel Prize. Don't worry, Philip, it will be short. You tell me when I have 5 minutes to finish. So anyway, and then the point is, in order to improve the permeability, the goal is, I make the spoiler, just in case Philippe tells me to finish immediately. I tell you the end of the story. The end of the story is we are going to inject at high pressure. That will reduce a little bit the confining pressure of the system fractures. Second, we are going to inject very cold water, as cold as we want. In the simulations, I am assuming 20 degrees. So that the rock contracts, and contracting, since it is constrained, this is a mechanical effect, but when you contract, you don't become smaller. If you are stuck to an outer cake and the outer rock, the rock doesn't move, actually you move up and you open the fracture. So this is the second thing. So first hydraulics, second thermal, and third, in the water we inject, among the tracers, we will put a weak acid. Weak, not because low acidity, the acidity is the same as if 1 mole of acetic acid contains the same acidity as 1 mole of chlorhydric acid. Only the pH is much higher because it's not totally dissociated. And that means that the dissolution will be slow. So if we manage to get the water into the formation, it will dissolve at some depth, and that will ensure a relatively deep stimulation. So this is the end of the story. Let me show you the details. We expect to use a slightly fancier than that equipment, but that I put there just to know where we come from. But basically, so we will do this injection and extraction test. So we call the same test, we call it under different names. So first you inject hydraulics and extract hydraulics. So these are hydraulic tests, but in addition, we call them also push-pull tests, because when we push this water, inject, we add a tracer, and when we pull it, we monitor the tracer breakthrough. And we also call them thermal tests, because the water we inject is cold, and we expect the water to return is warm. And after completion, we expect to do also some CO2 push-pull to characterize irreversible fixation and improve understanding of the fracture block geometry, which is another topic which would also be very interesting, but it's not today's topic. Anyway, I'm going to show you some numerical and analytical results. By the way, some of your problems had analytical solutions, so you better compare with analytical solutions, always, otherwise it's not. And I'm going to do both the hydrothermomechanical and hydromechanical and thermohydromechanical. We are also doing chemical, but in our case, the chemical we are doing separate. To avoid, with Codebrite, we are using Codebrite for that. Theoretically you can, but it is a mess. So the chemical part we are doing apart. And I'm not going to talk about it. But just to get an idea of why these things work is, the analytical solution to the first hydromechanical problem. The hydromechanical problem is when you inject, and this is in plan view, this is in plan view, so borehole, like the model you were showing. You inject water, so it's actually identical to what you were showing in for the hydraulics. So water expands, and it is somewhat counterintuitive that you compress in the radial direction, but you expand in the hoop direction, in the circumferential direction, which means this is something that all people doing fracking knows, that you tend to frack the well in the direction of the well, if it is properly oriented towards the stress state. Of course, we don't want to do fracking you know, fracking is a word that you should not mention at all. So we are not doing fracking. No, and the truth is that our injection pressures are going to be, yeah, 1/4 or 1/5 of what you would need for fracking, but still. But yeah, so that's the first thing. Now the point is, so is this, I call it arc-like behavior, like ring response, that you compress in the radial direction, you expand in the circumferential direction. One, you think it is quite trivial, but if you don't think about it, you are surprised initially. And when you add temperature, it's similar. Except that the thermal response is different in time, because thermal diffusivity is different from hydraulic diffusivity, especially in such a low medium. The thermal diffusivity is far larger than the hydraulic diffusivity, but mathematically similar. So this is more to stress that, to explain that when you push inside, you open the ring, and therefore you create these vertical fractures. Both cooling and fluid injection favor that. And the other thing is, but what about the horizontal fractures? So for the horizontal fractures, I recovered here some old work by Victor, who was supposed to be here, but he couldn't do it. And basically the point here, again, I mean, on these couple of hydromechanical problems, I don't dare to get into them if I don't have a clear vision. The point is, if I am injecting fluid in a low permeability or with high pressure into the formation, who is standing this force that I am applying? I am pressing the formation with high pressure. How does the rock resist that? And the way the rock resists it is, I don't know how to explain it, but there is again also an arc-like, although now since it is radially symmetric, it's more like a vault, like a cupola type. Now you look at San Marco Church to think of how is that standing, and it has this vault type of shape. If you press the rock, compresses expands radially in this area blue and compresses in the brownish area, which when you look in the vertical direction along the borehole, you can see that the vertical displacement is that's the vertical strain. So it's negative above the cap rock and positive below. So you have expansion and contraction. Now the question is, okay, so all this is going to happen. Will it be sufficient to create any significant effect? And okay, so for that we need to do the modeling with the best parameters that we have. So we do both 2D and 3D. I'm going to show only the 2D for simplicity, again with Codebrite. And so this is the vertical displacement we did with several fractures. I'm showing only the case with one fracture. Continuous line is only hydromechanic. And if you look, it's a pity that I cannot, but if you look here, you see that here there is a little jump. This is the location of the fracture. So there is a little aperture due to the hydromechanical effect. Notice the axis is, so this aperture would be, I don't know, 10 to the minus 5 meters. 10 to the minus 2 millimeters is not sufficient to create anything. However, when you do the thermal simulation, it is weird because you see the lower part moves up, positive displacement up, the upper part moves down. So this is the color scale. So the upper part is moving up, the lower part is moving down. It looks like it is closing. The upper part moves down, the lower part moves up, it closes, but in reality it really inverts here. And this is what I was calling the arc-like effect. I spent so much time explaining all this thing about the arc-like in the radial direction, the vault-like in the horizontal direction. This is the sphere-like in this area. In this area you have a sphere-like response. So cold water enters into the fracture tends to expand, tends to open, but at the same time you have to increase the stresses to resist that pressure, and then you have like a little sphere resisting that. But the point is that now it opens a sizable thing, of the order of, I don't know, 3, 4, 10 to the minus 4, which is, I don't know, 0.3 millimeters. Come on, this will take permeabilities from 10 to the minus 15 that we were before to 10 to the minus 12, 10 to the minus 13, 10 to the minus 14, which, now we're in business. So this is the point. And then I am finished. So this is the aperture versus distance in the hydromechanical case. And when you compare with the thermohydromechanical, yes, it opens a lot, which was the point. Since I knew I was going to be late, I already told you the conclusion. Of course, the formations, stresses concentrate in the fracture. You have a very active region there. You can monitor all this. We will have an optical fiber to measure temperature along the borehole and also in time, so we can monitor where things are happening. And that's it. So we are ahead for a very exciting project, and I hope that perhaps not next year, but in 2 years, we will be here to explain to you how well this model works. Thank you.